Have you ever wished you had a kind of superpower? You know, the ability to see the invisible world that's all around us, like the heat shimmering off a road, or the actual shockwave coming off a jet? Well, today we're going to break down a scientific breakthrough that pretty much does just that. It's a whole new way of seeing that lets us not only picture these hidden forces, but actually focus through them in 3D. So, let's get right into it.
Okay, so take a look at this. This picture is the perfect example of the challenge we're talking about. That building in the background, it's not actually warped. That's the air itself around the jet engine, superheated and bending the light. These invisible disturbances, heat, shockwaves, you name it, they're everywhere. So the big question for scientists has always been, how in the world do you take a clear picture of something you literally can't see?
Well, to solve that, scientists have been using a really clever trick of the light for a long time. So let's break down this classic technique. It has a pretty technical name, background-oriented Schlieren. Let's just call it BOSS. But at its heart, the idea is kind of brilliant in its simplicity. Instead of trying to see the invisible thing directly, you just watch how it bends the light coming from a patterned background that's sitting behind it.
And the setup itself is way simpler than you'd think. All you really need is a camera, a background with some kind of detailed pattern on it, and then your invisible subject, like the heat coming off this flame, stuck right in the middle. And the genius of this is its simplicity. I mean, older methods required all kinds of complex lasers and mirrors. This approach made visualizing airflow so much more accessible. So how does it actually work? Well, think of it like a high-tech game of spot the difference. First, you take a clean reference photo of just the background. Then you introduce the disturbance. Let's say you fire up a jet engine in front of it. You snap a second photo. Then a computer compares those two images pixel by tiny pixel. The software hunts for any spot where the background pattern has shifted, and that map of shifts perfectly outlines the invisible flow.
And wow, the results you can get with standard bows are just incredible. On the left, you can actually see the complex little tornadoes of air, the vortices, spinning off a helicopter's rotor blades. And on the right, those are the sharp shockwaves blasting away from a bullet traveling faster than sound. We are literally seeing the shape of air currents and sound itself.
But there's always a but, isn't there? This amazing technique has one major limitation. A sort of flat world problem that's been a real headache for scientists.
Because here's the thing, reality isn't flat. These heat plumes and shockwaves, they're not just 2D cutouts. They are complex, swirling three-dimensional things. But all the images we've just seen, they're completely flat. And this quote from the source research really gets to the heart of it. A standard camera captures a single line-of-sight integrated quantity. Now that's a mouthful, but what it means in simple terms is that everything happening from front to back in that 3D volume just gets squashed or pancaked into a single, flat 2D picture. Let's just put it side by side. On the left is what the normal camera sees, one flat image. All the distortion is just mushed together. You have no idea if a swirl of hot air is close to the camera or far away. But on the right, that's the actual physical reality. It's a deep 3D volume where different things are happening at different depths. So how could you possibly capture that with just one camera?
Well, to solve a problem like that, you don't just need a better technique. You need a whole new way of seeing. You need a completely different kind of camera.
And this is where the story gets really cool. Because the breakthrough didn't come from changing the background or writing better software. No. It came from completely reinventing the camera itself.
Enter the planoptic camera. Now, its secret sauce is a little thing called a micro-lens array. Basically, it's a grid of thousands of tiny little lenses placed right in front of the camera's main sensor. And this setup lets it capture not just how bright the light is, but, and this is the crucial part, the direction that every single ray of light is coming from.
So the best way to think about it is like this. A normal camera is like having one big eye. A planoptic camera is like having thousands of tiny little fly's eyes all packed together. Each one sees the world from a slightly different angle. And it captures all that information, all those perspectives, in one single snapshot.
So because it captures the direction of light, the planoptic camera has an honest-to-goodness superpower. You can refocus the picture after it's already been taken. I'm serious. Imagine taking one photo of a landscape, and then later, sitting at your computer, you can decide, you know what, I want to focus on this flower in the foreground. Click. Actually, no, let's focus on the mountains way in the back. Click. That's the power this camera unlocks, and it is the key to solving our 3D problem.
Okay, so we've got our classic technique for seeing invisible distortions, and we've got this new kind of camera that can capture depth. I think you know what's coming next. Let's see what happens when we mash them together.
Right. This is the big question. What do you get when you take these two powerful ideas and combine them?
You get planoptic BOS. And its superpower, it takes that incredible refocusing trick we just talked about and lets you apply it to the invisible world. You can now computationally focus your way through a 3D volume of heat or air, isolating different layers of the flow, one by one.
Now, to prove this could even work, the researchers set up a really simple but brilliant experiment. They took their planoptic BOS system. For the disturbance, they just used two flames, one placed behind the other at different distances. And the goal was simple. Could the system take one picture and then, on a computer, focus on the heat distortion from the front flame and then refocus to see the heat from the back flame separately?
And the results were a huge success. I mean, it worked perfectly. On the left, when the computer focuses at the depth of the front flame, its distortion pattern is sharp and clear, and the back one is blurry. Then, using the exact same photo data, they refocus on the back flame. Bam! Its pattern snaps into focus, and the front one blurs out. They did it!
So this is the big takeaway here. For the very first time, a single camera in a single shot could digitally peel back the layers of an invisible 3D flow. That means an engineer can now see not just the flat shadow of turbulence inside a jet engine, but can actually focus through the complex 3D structure of that turbulence. This is a massive leap forward.
But as the researcher herself points out, this isn't the end of the story. This incredible proof of concept is just the beginning. It provides the motivation to keep pushing this technology, with the ultimate goal being a true, fully rendered 3D reconstruction of these invisible fields, all from a single camera.
And that leaves us with a pretty fascinating final thought. From making jet engines more efficient to understanding exactly how air flows over a wing, what other secrets about our physical world could we finally uncover if we could all just learn how to focus on the invisible?